Another example where we can apply principles of pressure, this is a problem that I'm rather fond of when we have a U-shaped tube that has liquid in both arms. Now, say we fill all this up with water. If we fill all this up with water, then the levels will wind up at the same height. If they were not at the same height, say if this is up here, then there would be a greater weight of fluid here, which would cause a pressure over here that's bigger than the pressure over here, and so fluid would flow to the left to compensate and equalize that pressure. If there's a net force on the liquid down in the bottom, it'll move. Where this can be interesting is if we've got this filled with water, but then we pour a little bit more, then we pour a little bit of something else on top here. We add some more oil to this side. And that's going to change the pressure, so fluid will flow. And what's over in this arm will get a little higher, and this will wind up being a little lower, but if this oil has different density than water, then they won't wind up coming back to the same height, because what has to be equal is the pressure down here. And for the same liquid, that means that if it's all one liquid, that means the heights will be equal, but if it's two different liquids, then the density of this oil has to be taken into account. And what's the same in this arm versus this arm is the total weight of the fluid. So let's do an example. Let's say we've added some kind of oil, but we don't know its density. So, but equilibrium occurs when the oil is 0.31 centimeters above the water level in the other arm. And then what we want to find out, and also the oil is 2.5 centimeters deep. We want to know what is the density of the oil. So, 2.5 centimeters of oil over here, and the difference in levels here, from the top of the oil to the top of the water here, is 0.31 centimeters. Now, we could go all the way down to the bottom of this tube, but we don't really need to, because from this point, where the bottom of the oil is, everything's the same. This is water, and so the pressure added by this water is going to be the same as the pressure added by this water, right? So basically, at this point, what we need to do is say that our pressure on the left must be equal our pressure on the right. At this point, this is where the 2.5 centimeters ends. Okay, at this point, the water, so this is going to be rho water, G, H water, and over here, we've got rho oil, G, H oil. Well, technically we have atmospheric pressure plus these, but the atmospheric pressure then cancels out. Our G cancels out, and so we can see that the rho of our oil is just rho of water times height of water over the height of the oil. The rho of water, I should have specified, let's say this is fresh water. Density is 1,000 kilograms per centimeter cubed. The height of the water is just the difference between these two. It should be in meters because this is kilograms per meter cubed. So we go 0.025 is the height over here, minus 0.0031. That is the height of the water over here, over the height of the oil over there, which is just 0.25 centimeters. Oh, that cancels out. I guess I could have just left it in centimeters because I'm taking centimeters divided by centimeters. But then we can do this out, calculate this out. 1,000 times 0.025 minus 0031 divided by 0.025. And we get that the density of that is 876 kilograms per meter cubed. If I consult my chart, 876, well, I guess that's somewhere between ethyl alcohol and olive oil. So I don't know what it is, but some kind of alcohol or oil, or I guess I said it was oil. Anyway, so that's how you can go about doing a problem like that. Pascal's principle says that if we apply a pressure to an enclosed fluid, that pressure will be transmitted to every point in the fluid. So if we have our same U-shaped tube thingy going on as we did before, we have it filled up with water or some other fluid. If we apply additional pressure to this side, that means the pressure everywhere in this fluid will increase by whatever amount the pressure increases over here. So now let's say we have our two arms, but they have different cross-sectional areas. Let's say this one's twice as wide. We'll call this A1. We'll call this A2. It has a cross-sectional area. And this cross-sectional area over here is bigger than the cross-sectional area on the other side. So if I apply a pressure over here, then that same pressure is applied over here. And pressure is force per area, so we can say that the force applied over here is the same as the force applied over here. If I apply a force downward up here, that's going to cause a force upward. This will exert an upward force on anything that might be on top of that over there. So, just following along the math, you can see that our F2 is equal to force 1 times A2 over A1. And we said that A2 is bigger than A1, so therefore the force 2 is bigger than force 1. And this is the principle behind what's called a hydraulic lift, which you may not have heard the term, but if you have like a car jack that'll lift up your car so you can work on the bottom of it, that's what they have in the mechanic shop. This is the principle that they actually use. You have some kind of pedal or something over here that you push down on this fluid, and then the fluid, that force is transferred through and it pushes this up, and you get more force out over here than you do over here. So by hand or with your foot, you can actually lift up a car if the area difference is big enough. Now that seems like you're getting something for nothing because you are increasing force, right? But that is not the case, because if we push down some distance d, call it d1 because it's over on area 1, then this will move up temporarily some distance d2. Well, this push down, the volume that's being pushed down over here is a1 times d1. The volume being pushed up over here is a2 times d2. So this actually moves a much shorter distance. So typically what happens with a jack is that you push down over some distance, and then the car will move up like a centimeter, or if that. And then the jack is set up so that it'll then catch in place right there. So then when you push down again, it'll ratchet up again another, small distance, and then gradually you can lift up a car or whatever to a height where you can work on it. Buoyant force has to do with the force on an object that's inside a fluid. So let's consider for a moment we've got our container, say it's full of water, and we just have, for simplicity's sake, we'll say we have a rectangular prism of plastic or wood or something, it doesn't really matter, submerged inside this water. So here we're inside a fluid, but we've got this thing going on. There's pressure exerted on all sides of this. There's downward pressure here, pressure going this way, upward pressure here, pressure here. The pressures on the sides cancel out, but on the top and bottom, we know that the pressure on the bottom is equal to the pressure on the top plus rho g h, because there's a height difference between the top and the bottom. And this rho g h, this pressure difference, gives rise to what we call the buoyant force. So the difference between these two pressures at the top and bottom is rho g h, and a difference in pressures is a force per area. Right? Oh, and we've got our prism, so these areas are equal. And if we set that equal to rho g h, we multiply the area over the other side, and then we have the difference in force between top and bottom is rho g h times A, which is rho g v. So this is the difference in force between the top and the bottom. We call this the buoyant force. So whenever an object is submerged in a fluid, there's an upward force equal to its density times gravity times volume. Now notice this right here is the weight of the displaced fluid. So however much, rho times v is the mass of the fluid, and multiplying that by g gets us the volume. This rho gv is the weight of the displaced fluid. So the buoyant force isn't dependent on the weight of the object, but rather on the weight of the fluid that is displaced. Now, the weight of the object does change something, because the weight of the object is proportional to the gravitational force on the object. So the weight of the object has everything to do with whether this will float if the buoyant force is greater than gravitational force, or sink if gravitational force is greater than buoyant force. But what the buoyant force is not dependent on the density or the weight or whatever of the object that is submerged. The fact that the buoyant force is equal to the weight of displaced fluid is known as Archimedes' principle, because it was discovered by a guy named Archimedes. And this holds true for any object, regardless of whether it's completely submerged or not. If an object is floating in the water, then the buoyant force acting on this object is equal to the weight of the displaced fluid, which will not be the total related to the total volume of the object, but the fraction of the volume that is submerged. So that always applies. Also, another way to think about this is if the same scenario, let's say that we just consider a box of fluid. So it's still all one thing. If we just consider this area of fluid, if this is all fluid, nothing would move. And so the gravitational force acting on this section of fluid has to be equal to the buoyant force on the fluid, or stuff would move around. So that's another way of thinking about Archimedes' principle.